Let's do a quick plot of the data. This data is going to be from the game minutes and the attendance. And let's do a quick plot of that. And label it RetroSheet Game Logs Scatter Plot Matrix. Let's run that. So here's the RetroSheet Game Logs Scatter Plot Matrix. If we want a higher resolution copy, we can export it. Y-axis is game minutes. X-axis is attendance, and you can see the range of attendance all the way out to 60,000. And this doesn't look like there's much of a relationship between attendance and how long the game goes. So right away we'd say there's not much to explore there, but let's go through the other commands here. Let's create a new variable that's going to hold the result of a linear model. Let's do a linear regression between game minutes and attendance. Game minutes and attendance. And that's what the LM function does, is runs a linear regression model for that. So let's run that. Good. So let's explore what these coefficients means in terms of our model. The coefficients give us an equation. Here's the equation that this data set tells us. This data set says minutes of a game equals 168.1 minutes at the start plus 0.00021 times attendance. So that means if attendance is 40,000, we get a slight bump up. There's a slight slope of this relationship upward. As we add attendance to the model, as we increase our attendance, we are at a very low rate going to increase the time of the game. If we express attendance in thousands, this equation becomes plus 0.21 times attendance. I'm going to do a subscript K here for every 1,000. So if I have 40,000, I have a slight increase in the time played. That's 40 times 0.2. There's a slight increase in the model. But that's what these intercept numbers and this coefficient number here represent. We can recreate the model from the data. Now, this doesn't look like a strong correlation at all. We'll click on this and run it. That's a very low R squared. What this is saying is less than 1%. 1% of the variability of the game minutes played, less than 1%, is described by the attendance. It's a very small factor. That's what R squared, the coefficient of determination, means. We can also run the correlation coefficient, R, that's 0.09, a fairly low correlation coefficient. But the data looks like that. The data is not that highly correlated. Even though there's a small slope in the line, there's not much correlation in this data set. In contrast, we can look at another plot and another set of data. And the question we're asking here is, does the number of outs correlate with the minutes played? Again, we're going to run a quick plot from ggplot2. Because it's over 2 lines, we're going to select both statements and run it. That ran. And here is the plot we saw earlier from the game logs scatter plot matrix. These are game minutes and these are outs. Does the number of outs impact the game time, the number of minutes that the game is played? Is there a correlation there? And so let's see. We have a new variable that's going to be the result of the regression test between game minutes and game outs. So we're modeling the idea that outs and minutes are correlated, and running a linear regression with the LM function and creating a new variable called time of game versus outs. Let's run that. It ran. We have a new variable TOGV outs to go with our TOGV attend. We can hit that command, show the intercept here. Now, what does this equation represent? What this equation represents is the idea that minutes of the game of baseball are starting with minus 5.388 minutes. That's the y-intercept. So the model starts with a little bit below, but it adds, for every out, it adds 3.362 minutes for every out. This is times outs. So based on the number of outs played in the game, you're going to add 3.362 minutes. So that's an interesting number. On average, through that whole decade, it took 3.36 minutes to record an out. And that's what this coefficient is saying. You take outs, you multiply it by this number, you add in this error correction term where the data crosses the y-axis at 0, where x is 0. So that's some interesting data. Maybe next time we watch a half inning, we see if on average it's about 10 minutes, which is what this says. 3 outs times 3.36 minutes. So that's what this equation shows. Let's again look at r squared and r to see what these data show. Okay, so we're looking at r squared. What this is saying is that including outs in a model that helps determine how long a game is played in baseball, including the outs in the model explains 37% of the variability of minutes. In other words, the variability in the length of the game, when we look at that variability in that data, 37% can be explained by including in our model, our explanation, the number of outs in the game. There's other factors too. It's not a perfect coefficient of determination, but 37% is the r squared value. Finally, we'll get the r value, the correlation coefficient. We'll run this final command, and the r value is 0.614, so that's r. That's the correlation coefficient between outs and game minutes.